All right, so Paolo asked me if I would talk about two different subjects. So I'm going to try to cram two talks into one, and I'll try not to go on too long. The first one has to do with gyrokinetic simulations. The second one has to do with fluid simulations. So I'll start with the gyrokinetic one first. What we're looking at is we're looking at turbulence in something called the levitated dipole experiment, which is kind of interesting. It's at MIT. It's 4.5 meters across, 3 meters high. It's got a superconducting magnetically levitated current ring that generates a dipolar magnetic field, and they've just started getting solid results. It hasn't been that long since they finally successfully levitated the current ring. And there's something really interesting about this system, which is surprising. And that is that in most systems, microturbulence, like ITG turbulence, for example, in a tokamak, tends to relax the pressure gradient away from the ideal boundary. So you've got a plasma, you want to make it ideal because you're just assuming that ideal modes are going to kill you. You've got residual non-MHD turbulence. This non-MHD turbulence tends to relax the pressure gradient, typically, driving the system further away from the ideal boundary. The shocking thing to me about this system is that in a dipolar geometry or related closed field line systems like a Z-pinch, the opposite, I'm going to argue that the opposite is true, actually, that what the microturbulence tends to do is drive the system into a state that's up against the ideal boundary. It will spontaneously steepen the pressure gradient until it is in the vicinity of the ideal boundary, where it will be then pinned by competition between ideal turbulence, which will be driving it away, and non-ideal turbulence, which will be driving it toward. And furthermore, the ratio of the density and temperature profiles are also going to be fixed by the properties of this non-ideal turbulence. So this is really amazing, and I've heard that one of the long ago was Hasegawa proposed the dipolar configuration as a possible fusion concept, just because it seems like the Earth's magnetosphere and other magnetospheres are pretty darn good at confining plasma. There are pretty steep gradients in the magnetosphere. They're long-lived, and so this has been an inspiration for the LDX experiment. All right, so there's a levitated dipole experiment. Just a picture of it. We need to do the modes that we're going to be focusing on are at the K-perp rho I of order unity-ish scale. So really we need a gyrokinetic model. There are in LDX there are collisions. It's sort of in a trans-collisional regime, not strong enough to justify rigorously any kind of ordinary fluid model. Anyway, so we're going to be using gyrokinetic simulations in a flux tube simulation domain. So just as in a tokamak, we're going to be simulating not the entire machine, but actually just the turbulence in a flux tube. And we're going to be using the fact that the turbulence is at very, very small scales. So and that allows us to look at just a portion of the machine rather than the whole thing. We'd love to do global simulations, but we can't. Numerically, that's too challenging at present. And to begin with, we're looking at electrostatic, beta much less than 1. Their highest betas are around 0.1. I think certainly eventually it'll be interesting to look at higher beta, although at least as far as the linear theory is concerned, it's not predicted that there's going to be that big a change when you raise beta, but we'll see.
So you turned off A parallel and built B parallel?
Right.
Yeah.
I think at the moment most of the energy is in a small population of very hot electrons. Does that make a difference?
Certainly there's a hot electron population and there's a thermal population. So you're asking me whether the hot electron population is changing? Yeah, they have observed, like their early papers, when the ring was suspended by a wire, didn't have very good confinement, and the plasma that they tended to get in there was dominated just by the injected hot electron species. They're heating the electrons preferentially, so the electrons tend to be hot, the ions tend to be cold. And so a series of papers were then written focusing on hot particle instabilities. Since then, once they've achieved levitation, they've gotten much better confinement. They actually think they're getting a particle pinch, and that's something I'm going to talk about. And so the thermal plasmas become much more important compared to the hot electron part. But there still is, TE is still larger than TI just because they don't have a source of ion heating yet. Anyway, so in this talk, I'm going to just I'll be talking about two different geometries. From the transport point of view, they turn out to be remarkably similar with a proper normalization. So remember, this is GS2. We're looking at the turbulence in a flux tube, and we're going to look at two flux tubes. One, which is a sort of strongly dipolar field line, which is typically where the LDX plasma sits. And then just for the purposes of understanding the impact of geometry, we're going to also look at a Z-pinch limit field line where you've gone very close to the current ring. And in that limit, everything becomes uniform along circular magnetic field lines. So that's a very nice theoretical limit. The direction around the magnetic field is an ignorable direction. So it's much easier than dealing with a dipolar field line like that. So I'm going to sometimes be talking about one kind of result or talking about the other, and that's because really, so far, it seems like every regime we've gone in, if you normalize things to parameters of the outboard midplane in the dipole, you get absolute levels of the transport that are within a factor of a few of what you get in the Z-pinch limit. And the reason why an outboard midplane normalization is desirable is the fact that in a dipolar geometry, the magnetic field is falling off like 1 over the r cubed, so the volume of the flux tube is actually increasing like the area times the length, which is r to the 4th. So typically, most of the plasma is sitting in a zone on the order of the midplane radius. Anyway, so those are two different cases. They're remarkably similar. The similarity, one of the things the similarity shows is that in the case of this field line, almost all the particles are trapped. 99-point-something% of the particles are trapped. In the Z-pinch limit, there are no trapped particles. Yet when you look at the movies, it's hard to tell the difference. And the transport levels are similar, like I said, with an appropriate normalization. And that's true over more or less the full range of parameters that we've looked at. All right, so as in a tokamak, you have, in this system, you have your ideal modes and your non-ideal modes. The ideal mode that you care about here is now just the ideal interchange. There's no magnetic shear in these systems. So it's just an interchange of flux tubes. The interchange mode has a natural growth rate on the order of CS over the square root of RLP, just like a ballooning mode would. This term here comes from plasma compressibility. When you take the divergence of the E cross B drift, there's a finite term due to the fact that the magnetic field has a 1 over R variation. And this is stabilizing, this compressibility is stabilizing. So as a result, you can stabilize the ideal interchange if your pressure gradient is weak enough. So weak pressure gradients mean large LP. So if LP is in a Z-pinch, for example, satisfies this condition, you're stable to ideal interchange modes. You're not stable to other kinds of modes, in particular to entropy modes, which are the modes that I'll be focusing on, which are sort of K-perp, rho I of order 1 modes, but you are stable to interchange modes. And this is an expression for the Z-pinch. There's a more complicated but analogous expression for that in the dipole involving averages over the magnetic field. It's not very illuminating, but it's similar. So this entropy mode, I have never heard of the, yeah.
Barrett, are you saying that criterion stabilizes the interchange modes?
Right.
So it is stable in this system.
Right. So we're going to be focusing.
You're focusing because those modes aren't unstable.
We can't study ideal modes with GS2, right? Because ideal modes are going to cascade to the largest wavelength in the box, just as you couldn't study ideal ballooning modes with DBM or GS2. So we're gonna assume that the plasma is in a regime that's ideally stable. So we're going to assume that this condition is satisfied, and then we're going to look at the transport due to non-MHD modes. So analogous to what we do in the tokamak. And really the logic behind this is that usually if you're unstable to ideal modes, your confinement is really bad. So whether or not they're there yet, that's certainly where they would certainly like to be operating in an ideally stable regime in order to have good confinement in their machine. All right, so I had never heard of entropy modes before. These things are, I will say, the most challenging numerical thing that I've ever dealt with, but at the same time, they're very interesting. So there's some weird stuff that I'd never seen before, but it's very interesting. Anyway, this just shows some numerical growth rates as a function of k rho s. The growth rates go to 0 at long wavelengths because they're not ideal modes. They have peaks at k rho s, which rho s, ti over te is like rho I, on the order of 1, and they have growth rates that are on the order of the ideal growth rate, cs over the square root of RLP. That's true even though we're in an ideally stable regime. Okay, so that's kind of interesting. We're in an ideally stable regime, but we've got non-MHD modes that have growth rates comparable to the ideal mode. The catch is that they only have growth rates that are comparable to the ideal mode at very small scales. Okay, long scales, the growth rate tanks to 0. All right, algebraically, these things are pretty complicated, but for reasons I'll be explaining later, these modes are driven by a gradient in the specific entropy, which you can write as either for collisional plasma P over n to the 5/3, or if you write P is equal to nt, this is also T over n to the 2/3. And really, one of the punchlines of the talk I'm going to give today is the entropy mode. What it wants to do is it wants to drive the system to a state in which this is constant. It wants T to be a constant times n to the 2/3, or P is equal to a constant times n to the 5/3. That's what this mode wants to do. It wants to drive the gradients toward that state in which the specific entropy does not depend on position. And whether you've got a gradient of the specific entropy that's positive or negative, either way, the transport is going to drive the entropy, this quantity back to flatness, whether it's got a negative radial gradient or a positive radial gradient. Furthermore, I won't go into details because of the time. These things can drive pretty whoppingly huge transport. If you write a particle or heat or transport as like n times some average effective velocity, you get velocities on the order of 50 meters per second, or in some regimes a lot more. 100 is possible. I mean, you wouldn't necessarily expect the machine to ever operate in that regime because the transport would just be too large. But it is certainly, these modes, 4 LDX parameters drive experimentally strong transport. But they're not really sure in LDX whether these modes are operating. They've observed them, but that's about all they're ready to say so far. When I called up Jay Kesner recently and asked him about, what do you think, Jay, what do you think about the role of entropy modes versus ideal interchange or other things? And he said to me, we just don't know yet. We don't have enough data. We're going to be looking at it. So I don't, experimentally, the importance of the validity of what I'm going to say and the relevance of it is up in the air at the moment. All right, so here's a typical GS2 simulation run by Sumi Kobayashi, my former student. And so the radial streams broke up. I'll show it again here in a second. Maybe I should start it from the beginning again. All right, so here's the linear phase, right?
What are these stats?
There. Oops. Oh, that is some kind of transient. It's funny. I thought it would pause. It doesn't seem to pause.
There's some weird fast.
Well, the way the normalization works is that the normalization, as the modes grow, the normalization of the plot changes, so that the first frame, those were like infinitesimal little perturbations. And then the thing grows exponentially. But you can't see any of that because the normalization of the plot is being continuously changed. Anyway, so these blobs are nonlinear entropy mode transport. You notice one annoying feature of this mode, which is that it has both large scales and these tiny little scales here. And that's a symptom of the fact that the growth rates tend to remain robust up to fairly high k rho I, making it a challenge to simulate. So anyway, so that's a typical simulation. All right, now here's where the entropy mode starts getting interesting. It turns out that there are two different branches of the entropy mode. A branch for when eta is greater than 2/3 and a branch when eta is less than 2/3. And eta is ln over lt. So when eta is greater than 2/3, what it basically means is that lt is smaller than ln. That means that the temperature gradient is steeper than the density gradient. Likewise, eta smaller than 2/3 means that the density gradient is steeper than the temperature gradient. I'm going to assume in both cases that the density and temperature gradients decrease with radius, as they do in the experiment. So here are results from GS2 that show particle flux, which is a normalized version of this, basically. Something I'll call the temperature flux, which is a normalized version of this in the case of the ions or in the case of the electrons. The lower axes here are eta, which are this parameter, ln over lt. So not surprisingly, 2/3 sits right about here. So the eta greater than 2/3 branch is everything to the right of this line. Eta smaller than 2/3 is everything to the left, okay, in all plots. Eta smaller than 2/3, greater than 2/3. On the upper axis is a parameter called d. Its actual definition is omega star I over a flux surface average of the curvature drift frequency. It's in a z-pinch, it becomes basically r over lp. But the thing about this parameter is that the most important thing you need to know about it, first of all, is that as d increases, so this is the d-axis on all three plots, as d increases, the pressure LP is decreasing. That is, the pressure gradient is steepening as you go up. So this is steep pressure gradient, and this is weak pressure gradient. And in fact, it's the parameter d that determines ideal interchange instability, which is just above this line here. The point at which the ideal mode sets in is a horizontal line, d equal to some number, I forget exactly what it is, but it depends a little bit on the model, whether you use CGL or whatever. Anyway, it's slightly above here. So if we were to push any higher than this, the system would go unstable to the ideal mode, and it would crash. Anyway, so here's the interesting thing. The units are crazy here due to some poor choice of normalization, but look, the thing you need to know is, as far as these fluxes are concerned, so these are GS2 turbulent results. Red is positive and blue is negative. Okay, so if you're in this color, that's about equal and opposite to this color. So now you go up and look at these fluxes and you see a very interesting thing. In the case of the particle flux, when you're at eta greater than 2/3, the particle flux is negative. Now, a negative particle flux means actually particles are being transported up the density gradient. The density is high in the center, low at the edge, and there is an inward transport of particles, in other words, a particle pinch, when eta is greater than 2/3. When it is less than 2/3, it's the opposite, it's positive. Particles are transported down the density gradient, which is the usual thing. So this area is essentially a particle pinch regime. It's a weird regime in which the particles transported up the density gradient. And the reason for that is that in this eta greater than 2/3 branch, the instability is driven by T prime. Now remember, eta is ln over lt, so when eta is greater than something, it means that T prime is bigger than n prime, so T prime is getting bigger. So it makes sense, in the large eta regime, T prime is the dominant player. It's the thing that's driving the instability. So the fact that the particle flux is negative isn't exactly crazy. I mean, if the density gradient were the source of free energy, this wouldn't make any sense whatsoever. The temperature fluxes, though, are positive. So here I've defined, like I said, here the temperature flux is defined in this way. In the eta greater than 2/3 regime, the temperature fluxes are both positive. And that makes sense because when eta, like I said, when eta is greater than 2/3, the mode is driven by T prime. So the mode is trying to relax its source of free energy. It's trying to flatten the temperature gradient, although it's perversely trying to steepen the density gradient. Eta is smaller than 2/3, it's the reverse. Instead of blue, red, red, you have red, blue, blue. So in the small eta regime, the particle flux is positive, but and in that also makes sense because for small eta, you mainly have density gradient rather than temperature gradient. But the temperature fluxes are negative in both cases. Okay? Yeah.
When you say use the word branch,
Yeah.
are you using that in technical sense of being related to a linear dispersion relation, or is it just to qualitatively describe these different regimes that you observe in the flux?
The growth rates, let's see, do the growth rates actually go through 0 or not in that? Do you know? You remember? I think it is a distinct branch as far as in the linear sense. I think it is.
Linear theory hasn't been done.
Well, there's a few things. First, all the analytic linear theory has had to assume k perp rho I is much smaller than 1. And in that limit, the MIT group has done some gyrokinetic studies. We've also looked at Berginsky and gyrofluid.
So,
And the dispersion relations are pretty complicated. There's, like in the gyrofluid model, it's like a millionth order polynomial or something like that. You remember? And then, so, this is the first study that's ever looked at these modes non-linearly. Linearly at high K, we've also, right, Paolo wrote a great gyrokinetic solver that agrees with GS2 to study the high K linear properties of the mode.
Is the field curvature and the tracking of the particles essential in this? I mean, could you mock up a simple straight field that has density and temperature gradients and recover this kind of a result, the century mode? I mean, it seems like one could simplify the problem and identify at least a little bit more about the physics. I mean, as you say, it's very difficult in this real system where you've got curvature and everything else playing a role. But, I mean, the way this looks, it looks just like atmospheric turbulence.
Yes, you're right.
Is driven
Which
by
one? P over rho to the
entropy
gamma.
gradient.
Yeah.
And so it seems like you could just develop a straight field, sort of a Cartesian kind of atmosphere thing, and see what you get. And you could do that with gyrokinetics and probably get a lot more detail out in terms of how this works, at least in that straight field. It's certainly going to be modified by curvature.
It's possible. I'm not sure, although I'm later going to.
Has anyone tried that? Do you know? Or?
No. This is the first time the system's been explored.
Yeah.
I am going to explain, for example, I'll take you through a linear calculation that shows where this negative particle flux comes from, and the curvature does enter in an important way. The curvature drift frequency enters in an important way in that calculation.
Okay.
So, I'm not sure.
When you look at your D parameter,
Yeah.
R going to infinity means D going to infinity. Now, the question is whether there's other things that enter independent of that ratio.
Yeah, I guess.
Right, because that first parameter was that curvature.
Let's talk about that. It's an interesting question. I'm not sure.
Question can I ask
Yeah,
is,
sure.
You've written it this way, but what about just looking at the entropy flux?
Oh, so the entropy flux was always going to be, I'll show this in a
It's always
second.
positive, right?
Yeah, okay. Yes, it's always positive. So suppose we write the entropy like this, T over n to the 2/3. And now you compute the gradient of the entropy. There's, of course, obviously the density term here with the 2/3 and temperature term. The radial gradients are both negative, so I'm going to replace this by minus ln and this by minus lt. So this is equal to this. All right. So when eta is smaller than 2/3, that means that this is smaller than this. That means that this term is bigger than this term. So this is positive, with this being the winner. And so therefore ds, this quantity is positive when eta is smaller than 2/3. Now think about the transport. In the small eta regime, the particle flux is positive radially. That positive transport relaxes the density gradient. That means ln increases, whereas the temperature flux is negative. That means the temperature gradient steepens, so LT decreases. So this term is bigger than this one, because eta is smaller than 2/3, but ln is increasing, so this is getting smaller, and LT is decreasing, so this is also making dsdr smaller. So both of these trends are driving the gradient of the entropy down towards 0. The opposite is true in the eta greater than 2/3 regime. In that regime, this term is bigger than this one, so dsdr is actually negative. In that regime, the density transport is negative, so that causes the density gradient to steepen, ln to decrease, whereas the temperature transport is positive, so LT increases. So this term is getting bigger, and that term is getting smaller. And what that is doing, since the entropy is overall negative, it's driving dsdr. dsdr is negative, and it's being driven back towards 0. You got to kind of think about that for a little while, but that's what it does. So it seems to me that that in either case, what the transport wants to do is it wants to make dsdr equal to 0, which is eta equal to 2/3. So that's what's special about eta equal to 2/3. When eta is equal to 2/3, the entropy gradient is 0.
So does that mean that the flux of entropy is positive in all cases? Is that right?
Right.
But have you done similar plots to the previous thing with entropy?
No.
No, it hasn't, but no, what you-
Oh, it could be. Just haven't done it. I've looked at, so far, we've only looked at the density transport, the temperature transport, the heat transport. The heat transport is basically the sum of the particle and the temperature transport. And it's usually positive, except in certain exotic cases. All right. So recently, the MIT group published a Nature physics paper, and in which they argued that the profiles in LDX, similar to the profiles in the magnetosphere, actually are sitting in a regime where eta is on the order of 2/3, and they're close to the marginal ideal stability boundary. So in other words, this region, I could have made the circle bigger, somewhere in here. And that actually makes sense from the point of view of the transport. I guess I don't. That actually makes sense from the point of view of the transport. Suppose that your discharge is sitting here. It's stable. You're fueling it. There's no turbulence, so the gradients start to steepen. So the pressure gradient steepens, which means you go up in D. All right, so now you're sitting in here. The particle transport is negative, and which is why this is blue. This is the particle transport. The temperature transport is positive. The fact that the particle transport is negative means the density gradient is steepening, so ln is decreasing and LT is increasing. That means that eta, which is ln over LT, decreases, right? The negative particle transport steepening, the density gradient, so this is getting smaller, this is getting bigger. So what happens is, if you enter this region, the transport is going to drive you to the left. So suppose you go in here, the transport drives you to the left. You then get stable again. This profile steepen up. That increases the pressure gradient. You go up, and then it drives you to the left again. So the bottom line is here that there's going to be a natural tendency of the discharge to want to move up and to the left in this figure. The opposite is true when you're in this region. When you're in this region, now the density gradient is driving the turbulence. The particle flux is positive, and the temperature flux is negative. The positive particle flux means that the particle gradient is getting smoother, ln is increasing. The temperature flux means the temperature is steepening up, so LT is decreasing. So the turbulence is now trying to increase eta. So again, it's going to be now up and to the right, up and to the right, up and to the right. So our prediction is that the natural state for transport for the profiles would be roughly what they claim to see in this paper, eta equal to 2/3 on the order of 2/3 to the, their measurements are not that precise yet, and near the ideal stability boundary. Now, when they wrote this paper, they didn't know anything about these results. They argued in the Nature paper that that the plasma sitting there may result from ideal interchange turbulence, and there's two components to that argument. One component is that naturally ideal interchange turbulence is going to drive the system toward its marginally stable state, which is approximately somewhere along this line. As to eta to the 2/3, they get that via an argument that is, I'm not going to take the time to explain. Maybe it's right, I'm not sure. It's kind of a hand-wavy argument as far as I'm concerned, but it might be right. Anyway, maybe what's happening is both the ideal modes and the non-ideal modes are all trying to push the system into that position. It's quite possible.
More theory was needed, not more observation.
Well, like I said, I asked Jay point blank, could the results you report in this paper be due to entry mode transport? And he says, we don't know yet. But it's not, he wouldn't rule it out. He said it's possible. And here the physical origin of the pinch. It's actually not as bad as it looks. So here's the density equation. Here's the E cross B drift. The fact that B is varying with position, if you just fast forward down to this line, gives you what's known as the curvature frequency omega d, which is this quantity here. So this is just for the particle pinch regime, just to focus on one particular case. So in the regime of the particle pinch, which is this eta greater than 2/3, it turns out that this is the dominant term in the density equation. And what it means is essentially that n is equal to minus a positive constant times v. N wiggle is minus positive constant times v. So that means when v wiggle, the radial velocity is positive, n wiggle is negative. So here, Vx is positive, but delta n is negative, and vice versa. When v is negative, n is positive. So you're convecting a high density in and low density out, which is the reason why you're getting a particle pinch.
So this seems to have some, at least vague relation to what people call the turbulent equipartition pinch and tokamak.
Turbulent equipartition pinch. I'm not familiar with that.
Well, the origin is that it's the same as you're mentioning here, that mod B varies in space. So the divergence of the E cross B velocity is zero. People then go on to various arguments talk about a pinch.
Yeah, so that's right. So in the general gyrokinetic literature, for example, I've seen people refer to things, there are two different pinches. There's a curvature pinch and there's a thermodiffusion pinch. They're driven by different terms in the density gradient. This is a curvature pinch in the standard lingo, which comes from a gyro. So you can do the quasi-linear theory. So let me just say, this pinch, whenever you see the pinch non-linearly, you also see it linearly. So the particle flux in this eta greater than 2/3 regime, even in the linear phase, is negative. Just goes zooming on down, decreasing exponentially, and then just saturates. So quasi-linear theory apparently has in it some physics that's consistent with this pinch behavior. And you can do quasi-linear theory, which is a fancy version of what I had on the previous slide, and it works very well. If you do a cut through here, when you enter this negative particle pinch zone, the quasi-linear theory predicts a negative particle flux. When you do a cut across here, the gyrokinetic quasi-linear theory predicts a positive particle flux right where it's positive, and then a transition to negative right where it's negative. So that seems to work very well. Yes? in the quasi-linear analysis is the
Not only for the linear, but also your GS2 analysis, you assume the background distribution function is
a Maxwellian.
Maxwellian.
Yeah, in GS2, the background distribution function is assumed to be an isotropic Maxwellian.
But at the beginning, you mentioned the large fraction of the particle in the sample configuration. Does it have any impact on the equilibrium distribution?
On the equilibrium distribution.
So,
Well, we're at very low. We're at very low beta. So, to a first approximation, the magnetic field is just a vacuum field. But you're right in that almost all the particles are in the dipolar case are trapped. And those are contained in the GS2 has those. GS2 treats trapped particles, so those are present in the simulation as they would be in a tokamak, for example.
So experimentally, like, how do one distinguish between interchange turbulence and gyrokinetic?
The scale length. So these modes will have k rho s, 0.2 or something. It will be tied to the wavelengths will be tied to rho s. Will be short. Ideal modes will be global. Yeah. So they see they see what they think are these fluctuations. They're in the right scales and frequency ranges. They just don't know what. Yeah. Yep. Well, I'm eager for them to study these more. Anyway, so summary for this part of the talk, which means the next part of the talk is going to have to be pretty short, is, but that's okay. I'll have to go through it quickly. Entropy mode transport is expected to drive LDX toward marginal ideal stability in 8 = 2/3. Now, in a dipolar field, just to be more specific, you can show that ideal stability, that's sort of that vertical line I was referring to earlier, corresponds to PV to the gamma is equal to a constant, where V is the volume of a flux tube of a given fixed amount of flux. Now, since B goes like 1 over r cubed, the flux tube area increases like r cubed. The volume is like the length times the area, so the volume goes like r to the 4th. So this condition, which comes from marginal ideal interchange stability, so that pinned up against that horizontal line, means essentially that P goes like V to the r to the minus 4 raised to the 5/3 power, which is r to the minus 20/3. The entropy mode wants P over rho to the gamma is equal to a constant. Comparing these two things, you can see that that just means that n times V has to equal to a constant, so n goes like 1 over r to the 4. So these are sharply peaked profiles. That's the message here. The temperature over n to the 2/3 is being driven to 0 because that's eta equal to 2/3. So temperature would go like that. Anyway.
Can I ask something?
Yeah.
I'm not still understanding your logic.
Sure.
It's very clear that this instability drives it to 8 = 2/3.
Right.
If you start off with a system with exactly 8 = 2/3, it's not at all clear to me that it will drive it towards the ideal stability boundary.
Well, all that you'd expect, so if 8 = 2/3 are, suppose that you were therefore stable to ideal interchange and entropy mode,
Yeah.
and you're fueling it. So it seems to me that both gradients are going to start to steepen. So the pressure gradient.
Yeah, but your statement is that entropy mode transport is expected to drive LDX towards marginal ideal interchange stability.
Right.
Your gradient is really driving it towards 8 = 2/3.
Well, I had two parts to that argument actually. I was arguing that the transport drives it to the left in this region, to the right in that region, so that's consistent with what you just said. But if you just go to the left or the right, you're going to enter the stable zone. Once you enter the stable zone, the profiles are going to start to steepen up, I'm assuming. This is just an argument. I don't know if this is true. This is my logic here. My logic is that the density and the temperature will start to steepen up, or at least one of them. If you're fueling the machine, there's no turbulence in the machine.
Okay, but that's not the entropy mode. So you're talking about other mechanisms which will steepen. If you have other mechanisms to steepen, and then you combine that with the entropy mode. But the entropy mode itself
The entropy,
As far as I understand, doesn't really.
the entropy mode, no, you're right. It's what it is the fact that there's this, it's V-shaped. That's the key.
So you have to fuel near the same speed. And if you were fueling from the edge, then would it be
Yeah, if you had a reverse gradient,
if you fuel at the edge,
yeah.
should this mechanism work?
Well, I assume, yeah, so all these were done in the context of decreasing, radially decreasing N and T profiles.
So what happens?
Not sure what happens if you reverse the sign of one of the gradients. I imagine you would get some interesting.
What happens if you're exactly 8 equals 2/3, but you're above D equals 3.2?
Then
Why
you're-
is that unstable?
Then that's unstable to ideal interchange.
Oh, so that's the other
Yeah.
mode there. Okay.
Ideal interchange lives basically everywhere above this horizontal line.
All right.
And why was this, you said this is the hardest mode you ever looked at, so what's going on?
Because of the scales, it
Scales?
has really, really short scales. Particularly in the Z-pinch, the growth rate just goes up and then it like flattens out.
So how do you deal with that when you're on high D?
Well, it's difficult. The first thing, when we first, well, it can lead, GS2 had a lot of trouble running in this zone. So it actually, we went
Did you
through,
put some viscosity to shut it off? Or was it-
when we first did this, we ran with, we had to put in, if we didn't put in this was kind of weird. The dipole, when you go to the 3D dipolar system, the code seems to run fine without any hyperviscosity. When you go to the Z-pinch, there's something about the two-dimensionality of the system that is, depriving the system of some sort of damping or, energy channel. And so there seemed to be some sort of accumulation that would lead to a very slow but long-term climb in the gradients. And if you put in a little bit of hyperviscosity, you could get rid of that. That led to, and so there's been work done. It turns out now you can get the same result by just, with the new and improved GS2 collision operator, you can get the flattening with just some collisions, although you couldn't back when we originally started looking at this. So it's mainly it's the separation of scales. For some reason, GS2 does not like to run if you try to increase the box size beyond a certain amount, weird stuff starts happening in GS2. And this mode is approaching that longest scale that we can simulate. The growth rate starts to go haywire and Bill said, oh, well, I've seen this before. Usually you turn this and that knob. We turn this and that knob and it doesn't help. It's been a real pain.
Box size, you mean Z, because these are linear calculations.
I mean X and Y,
Oh, X and Y, okay.
yeah.
For the 3D.
Yeah, particularly for the
These are
dipole.
linear calculations, or are they not?
No, this is a nonlinear. These are
Oh, this is
nonlinear. This is
nonlinear.
nonlinear transport.
All right. Okay.
All right. So just, I don't know whether I should even bother with, since I've used up practically a whole hour with this. The other talk was actually about LAPD, which we were just hearing about. So Paolo and I have been simulating that in this case with a Brzezinski model. So Paolo wrote a wonderful code to evolve these equations. So they have sources in the density and the temperature. They have sheath boundary conditions at the edge. These sheath boundary conditions, I could go through them in detail. I'll just explain the physics of them. Basically, if you're right at the thing about, so now most of us aren't used to simulating systems in which the field lines are in contact with the material wall. And in the situation where they are, there's a problem, because if you're right, if I've got a magnetic field like this, I got a bunch of ions and electrons here. Basically, the electrons, half of them are going to have a thermal velocity in that direction, half of them in that direction, so this half, right, which are right next to the wall, are going to hit the wall and leave the plasma. There's similarly going to be ions, same thing, half of them going that way, half of them going that way. Only because the ion thermal speed is much lower than the electron thermal speed, the electrons are going to be leaving the plasma much faster than the ions. Well, suppose we let them do that. that means that if we started with a quasi-neutral plasma, the plasma is going to charge positive because there's more electrons leaving than ions, which if that means since the plasma is charging positive, that's going to be holding back the electrons. After a while, the electrons are going to start to say, well, there's an electric field that's trying to keep me in the plasma. Maybe I won't leave quite so fast. And then there's a critical value of that electric field when the fluxes of the electrons have been slowed down enough by the electric field, and the ions conversely are accelerated by the same thing, such that the fluxes are equal to the wall. So there's a magic balance you need between, in this case, the electron temperature. Ion temperature is smaller than the electron temperature in the machine, so it's mainly the electron temperature, and phi. And I could take you through the math, but basically the bottom line is that in order to get no net current to leave your machine, you need the plasma to develop spontaneously a equilibrium phi profile that's proportional to the electron temperature. So if you have an electron temperature that looks like a top hat, you should have an ion temperature, a phi profile that looks like a top hat, with a constant of proportionality, capital lambda, which is about 3. The expression is right here. It's basically just a parameter that's taking into account the fact that the electron thermal speed is larger than the ion thermal speed. So it depends on the mass ratio, but logarithmically, typically it's about 3 or 4. All right, so here I'll show you some simulations. There's n, I have n, t, e, I have phi t, which is about equal, phi is about equal to lambda t, and n. I'll just show you t, all the movies look very similar. There are actually 2 kinds of modes. So this is a cut through a 3D simulation. So the LAPD magnetic field is like this. You've got one end over here, one end over there, 17 meters long. Walls here that really don't make much of a difference for anything because no plasma ever gets there. The reason being that the plasma in here is streaming along the field lines essentially at the ion sound speed. Ions and electrons are both leaving. The plasma is being fueled, so the plasma is being replaced. So there's a simultaneously loss of plasma along the field. There's a transport of plasma across the field by turbulence. And then there's this input of plasma. There are 2 kinds of modes in here. There's a large-scale mode, which we've determined to be Kelvin-Helmholtz. That just grows. I said phi was like lambda t. That equilibrium phi profile turns out to be unstable to velocity shear-driven instabilities, namely the Kelvin-Helmholtz. There are also smaller-scale instabilities, which are drift waves in this system, and they're mixed together. You can kind of, you can see this mixture of large scales and small scales. These big blobs here are Kelvin-Helmholtz. But the fine scale structure you're seeing here is drift waves. And in a second, I'm going to show you movies of a 2D system in which we remove the drift wave. And I'll show you the difference. So
what is it that stabilizes the Kelvin-Helmholtz at small scale? Because the growth rates typically increase as K goes up.
No, typically what Kelvin-Helmholtz wants is its K spectrum is such that the most unstable wavelengths are comparable to the scale length over which the velocity profile varies. And if you go to substantially higher Ks than that, it's stable.
Oh, okay. Right.
And it's a global mode. It's a fully global mode.
Discontinuity.
Yeah,
Kelvin-Helmholtz.
yeah, that's
That one, of course.
That one's linear, and then I think flattens.
The parallel, there's not a lot going on in the parallel direction. There's Kelvin-Helmholtz should have K parallel equal to 0. Kelvin-Helmholtz does not like K parallel. Drift waves, on the other hand, do have finite K parallel. And if you compute the most unstable K parallel for the drift waves in this machine, you get K parallels that are on the order of the machine length. So, so there's sort of 2 different things here. There's some equilibrium variation that happens. The profiles tend to decline slightly toward the edges of the sheath. And then there are, apparently there are some drift wave fluctuations on top of that. They're not really obvious just by looking at this. And the time average profiles look like this. The 2 different curves are 2 3D simulations that I've been showing you up till now, 2D simulations that I'm going to show you in just a second.
What are the units, rho I?
Let's see. This is
Well, I imagine at the spatial or
rho s.
rho s.
All right, so to figure out, we have 2 modes, Kelvin-Helmholtz drift waves. Which is it going to be? Well, it turns out you can get rid of Kelvin-Helmholtz. There are two ways of doing it. You can, Kelvin-Helmholtz is driven by this term in the vorticity equation. You can either throw it out completely, or less drastic, you can replace phi by its azimuthal average. It's actually somewhat preferable to do that, although it's harder because by doing that, you preserve the spectrum of the drift waves, it turns out. If you just throw out this term altogether, that changes the spectrum of the drift waves, and we don't want to change. We want to leave the drift waves unchanged. We just want to remove the Kelvin-Helmholtz instability, and we want to see what happens. So here's phi and TE from a restarted simulation without the Kelvin-Helmholtz drive. So this is what the simulation looks like with the Kelvin-Helmholtz drive in here. And then when I click the button, the simulation will evolve without this term. And what you're going to see is that, you know, in this case, you've got kind of a blotchy profile. It's dark red here, and it falls off. After the movie is over, what's going to happen is there's going to be almost a perfect circle in here, which is all at this dark red color. In other words, the gradient is going to essentially, these profiles are going to steepen up right up to the source profiles, which were chosen to be a top hat, which is in the experiment. In the experiment, they fuel with a cathode-anode arrangement that has like a top hat-like plasma distribution. So the thing to watch for is this becoming a circle and totally uniform in color. So this little burbling is drift wave activity. Something weird is going on in phi. So as you can see now, the blotchiness is going away. You're developing a very, very steep gradient right at the edge. And so just keep your eye on this. This is the final time, which after this has started becoming very difficult to run. Look at, I'll just show you the comparison between this and the initial. So watch that frame there. See the difference? So anyway, so from this led us to think that it was really the Kelvin-Helmholtz instability that was responsible for the transport. We had another way to test that. If you can ignore k-parallel, if you assume Kelvin-Helmholtz modes have no k-parallel, they don't like k-parallel. You average the system over the parallel direction, which is only approximate, but you can derive a system of 2D equations that have in them the sheath boundary conditions and all that stuff. And then, in that system, there are only two different kinds of instabilities. There's a Kelvin-Helmholtz instability, and there's a sheath-driven instability, which I haven't talked about because so far we haven't found any regime in which it's important. But this is the result of the 2D simulation. This is the result of the 3D simulation with the same parameters. Everything you see here is going to be generated by Kelvin-Helmholtz. These are Kelvin-Helmholtz vortices. In this case, you've got a superposition of Kelvin-Helmholtz and drift waves. And what the drift waves seem to do is they act to sort of smooth out the fine structure you get in here. So the Kelvin-Helmholtz in 2D generates these really strong vortices. And in 3D, it tends to look more blotchy.
So how does the growth rate of that Kelvin-Helmholtz instability you see compare to the lifetime of an LAPD experiment?
Well, they have different ways of taking data. They can operate in the active phase,
Right.
which I think lasts like a few milliseconds or something, the pulse length. So I think that's many ideal, many Kelvin-Helmholtz growth times.
Right.
I don't know exactly. It's a long time. It's meant. I think that's a long. I think the duration of the active phase is long compared to the dynamics of all this stuff.
Like, do you have collisions in that?
Yeah.
Simulation?
Yeah. In fact, the drift waves are driven by the collisions.
It's hard to imagine an experiment with that kind of structure.
It is. Well, if all you've ever measured is the average.
Yeah, I wouldn't even know how to measure that.
Well, when you average these things, they just look like blobs. Time average them, I mean.
Yeah, right. 'Cause if your time scales are that much faster than the experiment, you're only taking 1,000 snapshots
Yeah.
or less than that in the experiment, you're probably going to have a lot less time resolution in the experiment.
Anyway, so that's, and the 2D, so not only do they, so when you compare the equilibrium nonlinear 2D profiles to the 3D case, they're pretty similar, blue and the red. So that's all.